Welcome to this explainer. I gotta tell you, I am absolutely thrilled to dive into this today because we're gonna completely shatter a pretty common illusion. We typically think of geology as this static, kind of boring list of rocks, right? A mountain is a mountain, a valley is a valley, and the ground beneath our feet is solid, permanent, and totally unmoving. But the reality is actually a mind-bending, active, ongoing investigation of a highly dynamic planet. Our world is constantly reshaping itself in real time. And today, we're going to uncover exactly how that happens.
Think about this for a second. What if the actual ground you're standing on right now has been traveling across the globe for 3 billion years? I know it sounds totally like science fiction, but it is an absolute scientific fact. The Earth's crust is not a single solid shell. It is in this constant, shifting, grinding motion, essentially acting as a massive planetary conveyor belt. To really get to the bottom of this today, we're pulling directly from the incredibly vast resources of the U.S. Geological Survey. We're tapping into over 140 years of continuous, rigorously peer-reviewed research that spans geology, natural hazards, oceans, and even planetary science. So this isn't just some theory thrown together overnight. It's a really profound scientific consensus built over more than a century of careful observation.
All right, let's jump right into Section 1, Mechanics of Plate Boundaries, or the gears of the Earth. So the absolutely crucial concept here is the lithosphere. See, the outer layer of our planet? It's not just one big uniform piece. It's this cooler, rigid outer shell, and it's fractured into 7 or 8 major puzzle pieces, plus a whole bunch of minor ones, called tectonic plates. And these rigid plates, they actually float and glide over a hotter, kind of squishy, ductile layer underneath them known as the asthenosphere. It's honestly like picturing giant, rigid rafts slowly riding on a super dense, incredibly hot sea of slowly moving rock. But here's the catch. Not all of these puzzle pieces are made of the same stuff. We've got 2 really distinct types of crust. On one side, you have the oceanic crust. This stuff is dense, it's heavy, and it's actually pretty thin, usually only about 6 kilometers thick at the ridges where it forms. Because it's so heavy, it sits lower down and forms our ocean basins. But then, on the flip side, you have continental crust. This one is buoyant and it is much, much thicker. We're talking up to 200 kilometers thick in some places. And this is what forms the land masses we actually live on. So you basically have these heavy, thin oceanic plates and these thick, buoyant continental plates, all just kind of mingling and interacting across the surface of the globe.
So what actually happens when these massive plates bump into each other? Well, they interact in 3 main ways. First up, divergent boundaries. This is where plates pull apart from each other. Think of the mid-Atlantic ridge, where brand new ocean floor is literally being born as magma rises up. Second, we have convergent boundaries. This is the collision zone. When 2 continents crash, they crumple upwards and form these massive mountain ranges, like the Himalayas. Or if a heavy oceanic plate meets a lighter continental one, the ocean plate loses the wrestling match and sinks, or subducts, melting right back into the Earth. And finally, number 3, transform boundaries. This is where plates slide and grind sideways past one another. The famous San Andreas Fault in California, that is a perfect example of this sideways grinding motion, which, as you probably know, famously generates some pretty massive earthquakes.
Okay, moving on to Section 2. What drives the plates? Let's take a look at the hidden engine.
Before we look under the hood at that engine, I want you to consider this number, 160 millimeters. That's exactly how fast the Nazca Plate, which is just off the west coast of South America, moves every single year. Now I know, that doesn't sound like much, but in geological terms, that is an absolute sprint. To put it into perspective, that's roughly as fast as your hair grows. Over millions of years, that tiny hair's breadth of daily movement literally shifts entire continents across the oceans. It's wild. So for the longest time, scientists kind of thought these plates just passively floated around on convection currents bubbling up from the Earth's mantle. But it turns out the primary engine is actually gravity. It's this brilliant mechanism called slab pull. Here's how it works. As that thin, heavy oceanic crust moves away from the ridge where it was born, it cools down. And as it cools, it gets even denser. Eventually, it gets so incredibly cold and heavy that it begins to sink deep into the mantle at one of those subduction zones we talked about. As this colossal, heavy slab sinks, gravity just pulls it down, and it essentially drags the rest of the entire continent-sized plate along right behind it. So the sinking edge is actually driving the motion of the whole plate.
Which brings us to Section 3, the plate tectonics revolution, a true paradigm shift.
Let's take a quick look at the timeline here. Back in 1912, a meteorologist named Alfred Wegener looked at a map, noticed that South America and Africa fit together perfectly like puzzle pieces, and he proposed this bold idea called continental drift. He even noticed matching fossils and rock formations on completely opposite sides of the ocean. But it took decades for the rest of the puzzle to come together. In 1947, Maurice Ewing's team found massive mid-ocean ridges, proving the seafloor definitely wasn't just flat. And then the real breakthrough. By 1963, Vine, Matthews, and Morley put the final pieces together by discovering magnetic striping on the ocean floor, which definitively proved that new crust was continuously being created.
But you know what's crazy? When Wegener first pitched this whole continental drift theory back in 1912, he was fiercely mocked by the scientific establishment. The fixist scientists of the day flat out stated they did not see how continental rock could plow through the much denser rock that makes up oceanic crust. They literally couldn't fathom the physics of it. I mean, they couldn't see how this buoyant, light continental rock could just magically plow through solid, dense oceanic basalt like some kind of giant icebreaker ship. And honestly, Wegener locked the how. He didn't know about the asthenosphere or seafloor spreading. Tragically, he died in 1930, way before he ever got to see his theory completely vindicated.
And that ultimate vindication, it came from what geologists lovingly call the oceanic tape recorder. See, when new magma erupts at those mid-ocean ridges and cools into basalt, the tiny iron minerals inside the rock actually align with the Earth's magnetic field. And because the Earth's magnetic poles periodically flip, the ocean floor ends up featuring this perfect, zebra-like pattern of alternating normal and reverse magnetic polarity, spreading outward symmetrically from the ridges. It acted exactly like a giant tape recorder, proving beyond a shadow of a doubt that the seafloor was indeed spreading and the plates were absolutely moving.
And that leads us perfectly into Section 4, Tectonics Beyond Our Planet. Is this a cosmic recipe for life?
Let's zoom out for a second and look at our cosmic neighbors. Take Venus, for example. It's roughly Earth's size, but it has absolutely no active plate tectonics. Why? Well, scientists believe Venus is just so incredibly hot that it completely lacks liquid water. And on Earth, water acts as a really critical lubricant for those shear zones that allow plates to slide past each other. So without water, Venus is just totally locked up. Mars, on the other hand, is pretty small. It might have actually had plate tectonics billions of years ago, leaving behind what's called a crustal dichotomy, but its engine basically cooled down and died, leaving it a frozen world. But here's the cool part. Incredibly, on Jupiter's moon Europa, NASA has actually found signs of ice tectonics. We're talking massive plates of ice that seem to be subducting right into a subsurface ocean. How amazing is that?
So this all brings us to a really profound hypothesis. According to top researchers, plate tectonics might actually be a completely necessary criterion for a planet to sustain complex life. Think about it. This constant recycling of the Earth's crust literally regulates our carbon cycle. When carbon builds up, it gets subducted deep into the mantle, and then it eventually gets released again through volcanoes. Plate tectonics acts like this massive planetary thermostat that has kept Earth's climate remarkably stable for billions of years. Without it, we might have ended up a boiling hothouse just like Venus, or a totally frozen desert like Mars.
Which leaves us with this final, truly mesmerizing question. Is a cracking, moving, shifting crust the ultimate requirement for complex life in the universe? When we search the stars for other civilizations, maybe we shouldn't just be looking for water or oxygen. Maybe, just maybe, we need to be looking for worlds that are broken, restless, and constantly in motion, exactly like ours. Next time you step outside, I really want you to take a moment to realize that the solid ground beneath your feet is part of a 3 billion-year cosmic journey, and it just might be the very reason you are even here to experience it. Thank you so much for joining me for this explainer. Keep asking questions and keep exploring.